that this is one of those cases where you might have questions before, during, and after the talk. Feel free to interrupt at any time. And can you share your screen?
Yes.
And Sarah, by the way, Aritra here is a grad student at the University of Minnesota. He's a statistician, and he has been working with Sarah Algeri. Sarah, do you want to say anything in introduction or some sort of a preface?
So you want me to introduce Aritra? I don't know.
Go ahead if you would like to.
No, it's just so Aritra is a PhD student here in statistics. We have been working on this project for a couple of years now. We encounter several challenges, and we know it's an important problem for both astronomers and particle physicists. We are primarily working in application in particle physics, but it would be great if the astronomers in the audience would point us problems where it could be applied, and or anything really. So feedback is very much appreciated. And well, I'm sure Aritra will address any of your questions. He has worked hard on this project. So yeah, that's all I wanted to say.
Thank you. Take it away.
All right. Okay. I think you just need to mute. So I'm Aritra. I'm a fourth-year PhD student at University of Minnesota. And so the project that I'm working on is semi-parametric signal detection under unknown background. It's a joint work with my advisor, Sarah, and our collaborators, Lydia and Oliver from NICHEF. So my plan for today is, let's see. Okay, so my plan for today is to briefly introduce our work, and then briefly go over the mathematical framework that we're proposing, the estimation and the signal search. Then briefly talk about something called the safeguard method, which is a existing widely used signal detection method, and then walk you through some results that we got, and finally end with some discussion. Okay, so whenever we are discovering any new physics, it's formulated as testing for the presence of a specific signal that you might be interested in the data that you are observing. However, rarely we have any scenario where you just want a signal and the data that you're getting is only from that signal. Often you have other nuisance signals coming from a wide variety of sources, and that constitutes the background which masks the signal of your particular interest. Therefore, the density of the data generating process that can be looked at as a convex combination for the signal density, which is of your interest, and the background density, which is unknown to us. So if the data generating density is F, it can be written as eta times Fs plus 1 minus eta times Fp, where your X is within a certain interval, which is your search region L to U, and eta is the mixing proportion of the signal, and we are interested in estimating eta. Note that eta can be anything between 0 and 1, and I have excluded 1 from the domain for the signal for eta, and that's because eta equals 1 simply suggests a scenario where your data set is all signal and no background, which is unrealistic.
Sorry, could I interrupt with a dumb question here? Distributions sort of convolve rather than add. So I'm not sure I understand the meaning of this linear representation of the densities.
So, yeah, what it simply means is that in the entire data set that you have observed, only a eta proportion of the data is actually coming from the signal, and the rest 1 minus eta is coming from the background. In physics, usually people write it as like the intensity function is written as the background plus some lambda time plus some mu times the signal, and that mu, which is the signal strength, that is kind of proportional to this signal proportion eta. It's just a different representation of the same thing.
Okay, I guess I'm still a little confused. I mean, so X, this is not time series, of course. X isn't time. It's the measured
Correct.
variable, correct?
Yes. Mhm.
And so,
X could be anything. So X is just the space where you are searching for the signal. It could be like it's any search region. Yeah.
right. So I'm thinking like in a time series, if you have a signal from a source and then a background, you're adding the processes, and the distribution of the sum of two processes is the convolution of their distribution. So wouldn't that be a better representation, at least for some context, than adding?
So when you add the signal and the background components, and we are not in a time series scenario. This is where let's say you have a particle accelerator and you are looking whether there is any Higgs boson production or not, and you are looking in the entire energy region between 110 to, let's say, 160, and you are interested in knowing whether there is a peak that has arrived at the 125 or not. And
Okay, I got it. And there's some assumption of independence of these two components underlying this. Is that?
yes, right, correct. So yeah, we don't assume that the background and the signal are somehow influencing each other.
Okay, great. Sorry to interrupt, but
Yeah, no worries. Yeah. All right. So at the end of the day, to know whether there is any signal in your data or not, remember the signal component is eta times fs. So you are essentially testing for whether eta is 0 against a alternative hypothesis, which is eta is positive. So in our framework, we assume that we do not have access to a background only sample, and we have no knowledge about the background density FB. And we carry out the estimation for eta using only the physics sample, which is the data generated from the experiments, which may or may not contain the signal.
But you do make the assumption that FB is different as a function of X to Fs, right? Because without that, you can just add.
Yes, FB is different from Fs. Yes, the fundamental nature of these two functions would be different. And as a matter of fact, we implement this in a bump hunting problem where signal is characterized by a peak as a bump in the search region, whereas the background is a relatively smooth looking function. So how we do it without knowing the background is we first start with the proposal background density GB, which acts as a proxy for the unknown density FB. And we don't claim that this GB is your background. It's just a starting point. And then we construct an orthonormal basis for all the functions in the square integrable space with respect to the function GB. And how we do it is we first start out with an orthonormal basis, and then we further orthonormalize that basis with respect to the function S1, where S1 is just a normalized version of the function S, and S is this Fs, our signal density, over GB, the proposal background, minus 1. And this S function kind of captures the deviation from GB in the direction of our signal density. Okay, So if this entire basis is this set is an orthonormal basis for the L2GB space, then the true background FB, the proportion FB over GB, can be expressed using this orthonormal expansion, which is 1 plus sum of beta j times the function tj's plus some delta times S1. And this delta now captures the departure from the true background in the direction of our signal Fs. And if we simply plug in this expression into our convex combination that we saw earlier, eta Fs plus 1 minus eta Fp, we get that F over GB, F being the true data generating process, F over GB can be expressed as 1 plus sum of tau j times Tj plus some theta times S1, where tau j's are simply 1 minus eta times beta j's, as you can see in the first brown block, and theta is eta times norm of that function S plus 1 minus eta times this delta. And these coefficients would be important in our development. So from linear algebra results, we can show that this theta is nothing but the integral of S1 df, f being our CDF of the true data generating process, and tau j's are integral of these tj functions in df. And now why we can estimate our theta and tau is because as a proxy of the CDF f, we could simply replace them with the empirical estimate, the empirical CDF, which is denoted by the script f. And if you simply replace it with that script f, this estimate becomes theta hat is simply the sample mean of S1 xi's, and tau j hat is simply the sample mean of Tj xi's. So theta and tau j, these are estimable. That's all fine. However, if you remember the expression theta, the last expression from this slide, which is theta is eta times this norm of S plus 1 minus eta times delta. If we try to retrieve eta from this expression, we get eta is theta minus delta over norm S minus delta. And the problem here is that delta is integral of S1 dfb. And delta cannot be estimated because, as we said, we don't have any information about the background and we don't have any data from the background only sample either. So this delta is non-estimable. So our alternative is that we completely ignore this delta from the expression. And as a result, we don't get eta, but we get something else, which is eta tilde, which is simply theta over norm S. And this can be estimated again, because we can simply replace theta with theta hat. And remember that how we calculate the norm of the function S is, it's just square of the, you square the function S integrated with respect to dgp. And in S, all that you need to know is about Fs, GB, and that's it. GB is our choice. Fs we already know. We are assuming that we completely know the signal density. So norm S can be computed easily. Now, it is easy to show that if delta is non-positive, then eta tilde is actually smaller than eta, which means the estimate that we are proposing, it's just a conservative estimate for the true proportion eta. Okay, that is when we can ensure that delta is non-positive. Yeah.
Delta is always positive.
No, delta can be negative as well. And that's our actually target, because delta is simply S1 integral of dfb. And the S1 function is actually coming from this S. And S is Fs over GB minus 1. So wherever, so Fs over GB can be smaller than 1. And the function S itself can be negative. So the integral is not guaranteed to be a positive value. Yeah.
So when delta is so effectively, you're considering the case when The signal is very small compared to the background.
Not exactly. So what we are trying to do is, well, it depends on a couple of scenarios, and we'll show how to. So this SDFB being negative depends quite heavily on what is the function you're using as your proposal background GB. And that's what we will tweak in order to ensure that this delta quantity is negative. So it's not very obvious how you can ensure that delta is negative. You can't just say this is the condition that you want, but we would show a mathematical argument and some heuristic approach to achieve that.
But if you're considering this as a ratio of Fs to GB minus 1,
Yeah.
The only way that Fs, when the Fs to GB is less than 1 is when GB is higher.
Yeah, well, we want the integral to be negative, and that can be achieved without making the integrand itself, that might not be negative always. In some region, it might be positive, in some region, it might be negative. But at the end of the day, we just want the integral to be negative, not the S function itself. It might be positive in some places. Yes. So we are integrating over the entire search region for our signal. So for example, in particle discovery, you know where, so if you're looking for the Higgs boson, you know where you can find the Higgs boson. It's supposed to be somewhere around 110 to 160. So that's going to be your search region in this case. And it can be, so the search region varies depending on your context. Yeah.
But you integrate over 110 to 130.
Yeah, exactly. Okay. Now, given that somehow we can ensure that delta is non-positive, what we are proposing is that instead of testing for eta equals 0 versus eta is positive, which was our actual signal search, we are proposing that you test for eta tilde is 0 against eta tilde is positive. If delta is indeed non-positive, then this is a more conservative test, because there could be cases where eta tilde is 0, but eta itself being larger than eta tilde is actually non-zero. So in that case, you might be missing out on signal. But there won't be a scenario where eta is actually 0, but eta tilde was positive. That's not possible. So that's why we are proposing the test eta tilde is 0 against eta tilde is positive. And if you remember from the definition of eta tilde, it's just theta over norm s. So it's the same as testing for theta is 0 against theta is positive. And the obvious test statistic for that would be just a z-test. Yes.
So I think you have to be a little bit careful here,
Mhm.
because hypothesis test is not probability. It's not logical. I understand you're using the conservative one, saying, well, if that one doesn't pass, then you apply the other. But it's known probabilistically that's correct. But hypothesis testing is not logical. You can have a testers that reject the one, but does not reject the consequence of that one. That is known there. So just want to know that whether how much the factor these results, that how do you imply the other one can be rejected at all?
Yeah, so what we do is we first build a setup where we are more or less sure that delta is non-positive. Okay, so we have created a scenario, we have created a proposal background GB where delta is non-positive. And if we are confident about that, then we are confident that this eta tilde quantity is actually smaller than eta, the quantity for which we are actually testing. And now, since we are testing for eta tilde, if it is 0, then there could be a case where eta is actually positive, but we would never really know. But if eta tilde turns out to be positive, then we are definitely sure that eta was positive, because eta was something that is larger than eta tilde. So we first ensure that we are in the regime where eta tilde is indeed a smaller quantity than eta, and then we move on to the testing for eta tilde.
I see yes, I understand your logic here. What I'm saying is, the hypothesis testing has this unfortunate illogical thing. What I'm saying is that, let's say you can actually test, you're saying your eta would be larger than, eta 2D, right? So if eta 2D is
Yes.
larger than 0, then eta has to be larger than 0, right? That's a
Right.
logical consequences. But what I'm
Yes.
saying that here's the weird thing about the hypothesis testing. You
Mhm.
could have that if you actually can do the test of the eta bigger than 0, using the same data set, you can have the following scenario that you will reject. You will reject eta hat equal to 0, which means you say eta hat is bigger than 0, but you do not reject eta equal to 0.
Yes, that
That's
could
possible
happen.
too.
Yes,
Yeah.
absolutely.
Okay.
And that's again, I mean, it's so that's that's a result of fixing your significance level at a certain point, right?
That's right. That's
Yeah.
exactly right. I guess what I'm pushing you eventually thinking about doing this from the Bayesian perspective, right? Doing the
Yes.
posterior, then you can make sure that at least the one
Yes.
statement is
Right. Yeah. So
consistent.
in this frequentist approach, we are hoping that we won't get such an unfortunate data set where you are facing those counterintuitive examples. You are in that 1 minus alpha non-type 1 error regime.
Yeah. Okay.
Yeah.
All right.
But the test for theta equals 0 is it's a simple z test, just theta hat over its standard error, and it's just normal 0, 1. So it's a simple enough test. And one of the main advantages of this test is that
Sorry,
yeah.
Is it obvious? What makes you think that it should be a normal distribution?
Oh, so that's because theta hat, if you look at the structure, it's 1 over n sum of S1 xi, so it's like a sample mean, and that just allows us to apply the central limit theorem and just use the z test.
But that does also assume that you have a large number of.
Yes, of course. Yeah, it's a large sample approximation. Yes, we assume that we have large enough samples. Yeah. And so one major advantage of this test is that, remember, our argument is based on where this theta is coming from. It's coming from this basis expansion, this orthonormal expansion, but the test never uses the basis functions, the other basis functions other than the S1 function. So it does not depend on the choice of your basis function. It does not depend on where you truncate this infinite sum. So it does not depend on any model selection. So it does not suffer from these uncertainties. It's just dependent on FS, GB, and that's it. Okay. So this is the test we are proposing. Now, the next obvious question is, you said that this test is conservative when delta is not positive, but how do you ensure that? Okay. So we made an argument for the bump hunting problem, where the background distribution is relatively a smooth distribution, and the characteristic of the signal is that it appears as a peak somewhere in the search region, as you can see with the blue curve over here. And our argument is that we would consider, so we would know where the location of the signal is supposed to be. For example, in Higgs boson search, physicists tell you that the distribution of the Higgs boson mass is a normal distribution with the mean at the 125. So we know the location of that distribution.
Again, do they say that it's normal because they don't know any better?
Well, as of now, we assume that we know the signal distribution. It could be that it's their limitation that they don't know the distribution any better. But as of our setup, we just assume that the signal density is completely known to us. Yeah. And what we do is we try to get a narrow enough region around that signal location so that it incorporates the majority of the signal mass. So for a very small number epsilon, I want a region m epsilon around this mu s, the signal location mu s, such that the area of this signal region is 1 minus epsilon. Okay. And what we can show is that, okay, now it's a big expression. So it's supremum of the true background over the proposal background, FB over GB. We split this inside the signal region and outside the signal region. Okay, so the green block, that's the supremum outside the signal region, and the red block, that's the supremum inside the signal region. So what we can show is that if epsilon times the supremum outside, yes.
So you said that it doesn't matter where you truncate your basis set.
Yeah.
Doesn't, I mean, isn't it important that the GB describe the background region well?
It should be just reason, like GB can be close enough to FB. Like you can experiment with a few density curves and just eyeball it so that it kind of looks like an okayish fit to the histogram that you have, and that is just good enough.
So I'm just looking at this figure that you had in the previous slide, where you have this what appears to be the Higgs boson segment of a like signal. If your GB is offset from that, wouldn't I don't know if it were lower, wouldn't the whole thing be considered part of the signal? I mean, would there be a
exactly
non-Gaussian tail, very heavy?
Right, we would get to that. So that's why we need to tweak the GB. And so I'm not saying that this is something we have with the GB that we start out with, but this expression leads us to construct what sort of a GB that we want.
I see.
Which is, so if we, so what we have here is epsilon times the supremum of FB over GB outside the signal region, plus 1 minus epsilon times the supremum inside the signal region. What we can show is that if this quantity is below 1, if this is bounded by 1, then your delta is non-positive. And how do we ensure that this is bounded by 1? So first, let's say epsilon is smaller. So that we can kind of ignore the first term for the time. Okay, so ignore epsilon times the green block for the time being. What we have is 1 minus epsilon times that red block. So if we can somehow ensure that what we have in the red block is below 1, so the supremum of FB over GB in the signal region is below 1, then that times 1 minus epsilon would also be below 1, right? And how can we ensure that the supremum of FB over GB is below 1 in the signal region? We would want GB to dominate our FB, our true background, in the signal region, in the entirety of the signal region, if not completely. The reason we can kind of get away with GB dominating FB in almost the entirety, even if it's not entirely, is because it's still multiplied with this 1 minus epsilon. So even if the supremum is slightly above 1, the 1 minus epsilon kind of offsets it, and we are still below 1. But we should remember that the signal region M epsilon should be narrow, so that GB doesn't have to dominate FB in a very wide region. If GB dominates FB in a very wide region, what happens is, since both of the densities have to integrate to 1, whenever you go outside the signal region, FB kind of shoots over GB. The first supremum in the green block, that gets extremely high, and epsilon times that is not negligible anymore. So what we want is a narrow signal region, meaning that your signal is localized enough, and GB dominates the true FB in the signal region. Now, we don't know what FB is, right? So one way to ensure that your GB dominates FB is to give GB kind of a wide bump in that signal region, so that we kind of assume that our true background is not extremely funny looking, right? It's not shooting up and down everywhere in the signal region. It's smooth enough. But in the signal region, if we keep a smooth enough and wide enough bump in GB, then GB would ideally dominate FB. So in that perspective, we don't really care about what is the relationship with GB and FB outside the signal region. All we want is inside the signal region, GB is above FB. And that's why I said an okay-ish guess for the background is good enough as long as we ensure there is this bump in the signal region. So one way to achieve that is what we do is we put two signal-like densities very close to each other inside the signal region. Those are given by this fs functions with mean set mu1 and mu2. And the sigma is the scale parameter, which is larger than what you have for your actual signal density. And you mix that with another function, QB, which is your primary guess for the smooth background. So for example, if this is what your data looks like, then you could probably guess your QB to be an exponential distribution and just mix that with two Gaussian densities, which are which have peaks very close to the endpoints of the signal region, so that you are putting two Gaussian signals very close to each other, and that kind of gives rise to this wide bump in throughout the signal region. And if you use a density like this, what you get is eventually something like this. So the red dashed line is our true background. The orange dashed line is our proposal background, and the blue line is the true density. So you see that GB is not really doing a very good job of approximating our true background outside the signal region. But as long as we can ensure that this orange line is dominating the red line in that signal region, we can say that it's good enough for us. Okay. And so what we have so far developed, it only uses unbinned data. But with physics, it's very common to get binned data, right? And with bin data, you have just bin midpoints and the bin counts. So we need to modify our estimator for theta hat, because theta hat was the mean of the S1 x-size being the precise observations that you made through the particle accelerator, let's say. So remember the definition for theta, it's just integral of S1 df. What we simply did was we discretized this integral, and we got, so for bin counts ni's and the corresponding bin mids xi's, we just discretized it and we got sum over ni S1 xi's over the total count n, which is sum of ni's. And we just plug this into our earlier expression for eta tilde, and we have a modified estimator for eta tilde as well. And as long as, again, we are ensuring that delta is non-positive with this approach, and we are still testing for eta tilde, we can claim that our test is still conservative. We are still in the conservative inference regime. Okay. The only difference that we should point out is that in this case, ni's are the random variables, which are assumed to be Poisson random variables. And in our earlier cases, those xi's were the precise random variables. That's the only major difference here. Okay, and for the bin data, again, one can show that this theta hat b is consistent for our true parameter theta. We further decompose our theta hat b in a way so that we get this new component, which is in the blue box. We call it theta check. And this theta check is 1 over k sum over ni S1 x-size, k being the number of bins. And again, we can show that the quantity k theta check over square root of this whole thing tends to a normal 0-1 distribution under the null hypothesis when your number of bins and number of observation kind of goes to infinity. So again, this is also an asymptotic test, but the asymptotic distribution we have is still a normal 0-1 distribution, and it's a simple enough test.
So what's T in this case?
So yeah, good question. T is, we assume that each Ni, the bin counts, that follows a Poisson distribution, which is, and the mean of that Poisson distribution is T times the integral of f on that bin. So T is kind of the overall average count that you are expecting in your entire region. Yeah. So as long as your T and K goes to infinity, this test statistic goes to a normal 0 distribution. Okay. Now, a little bit about the safeguard method. So safeguard method by Priel, and there is another method called the spurious signal method. These are two similar methods that are used at the Atlas collaboration for particle discovery. And both of them try to obtain a conservative estimate for signal, they try to estimate a conservative estimate of the background distribution to avoid false discoveries by accounting for signal-like fluctuations into them. And I'll get to what I mean by that. But as it turns out that might not be enough always. So in safeguard method, what they do is, so let's say they start out with a benchmark model, FB model, which is in the brown block over here. And into their final model, instead of feeding this FB model, the benchmark model, what they do is they first mix this benchmark model with the signal density, with again some mixing proportion epsilon. Okay. So this whole mixture, epsilon times fs plus 1 minus epsilon times FB model, this is fitted on a background only data first, so that they can estimate any parameters they might need for this FB model, and they estimate epsilon. So now the background distribution they have, which is, I'm denoting it by this GBSF, GB for the safeguard. So the safeguard background estimate they have, it has this signal-like component, which is supposed to account for a little bit of the signal present in the data, and that's how they try to be conservative. Now, even in the context of the safeguard method, remember that we could still expand FB over the GB for safeguard in the following manner. And there as well, we would have a similar term delta as we had in our case. Okay, so in their case, it would be their S function would look like Fs over their GB SF minus 1, and they would have a corresponding delta term. So how they actually fit their model is they fit the mixture eta fs plus 1 minus eta times their conservative estimate of the background. They fit a maximum likelihood estimation on the physics data, and they obtain eta hat MLE, the maximum likelihood estimate for eta. As it turns out that if this delta SF quantity is positive in reality, which the safeguard method cannot check, if this quantity is positive, then the asymptotic limit of the MLE of eta hat is actually positive, even though in reality eta is 0. So even when working with background only data, if they still end up with a positive delta, they can make a positive estimate of eta, and they can be claiming false discovery.
So how does it happen?
So we can show that, so the asymptotic limit for the maximum likelihood estimate eta hat MLE, which is eta star. So we can show that when in the actual model eta is 0, this asymptotic limit eta star still could be positive. So this eta star is not equal to the true eta. And that happens because, again, this is a misspecified model, because in reality, remember, the model is eta fs plus 1 minus eta times fb, which is different than the background they are using. So even if we have eta is 0 in that actual model, the asymptotic limit for their MLE still can be positive, because eventually they are not estimating eta in that true model. They're estimating eta in their misspecified model, where they have replaced their FB with their own version of the background. This is maybe I should have used some different notation. So let's say this model is alpha fs plus 1 minus alpha times their GBSF, and they're estimating alpha hat. The limit of alpha hat is not the same as the true eta. And even when eta is 0, this limit of alpha hat could still be positive.
That is the part that I'm having difficulty with.
Yeah.
Because when eta is 0, when alpha is 0, when there is no source.
Mhm.
Whatever you do to get an maximum likelihood estimate of
Mhm.
ends up being a description of the backup, right?
Yes.
So how can that lead you to think that there's a source?
That is because the model they're using, the mixture of the signal and their own version of the background, that is a misspecified model. This is not what is actually generating the data, right?
So, okay, so if you're saying that if suppose you have a power law background and you model it as a straight, as a horizontal constant model,
right? Yeah.
That would break down, obviously.
If that generates a positive delta, then that could.
And how would if it generates a positive delta?
Now,
how would it generate a positive delta?
It could generate in the sense, if the integral of this s function, this fs over gbsf minus 1 times fb, if this integral turns out to be positive actually, then
But you know that fs is 0.
no, fs is not 0.
In the case when eta is 0.
But fs still, fs itself is not 0. What we are saying is that the data generating process could simply be fp, and it has no fs component.
Yes, but that's the same as saying fs is 0.
No, that's different, because when you are fitting the maximum likelihood estimate, like when you are fitting that log likelihood still has that fs quantity. At the end of the day, you see whether that estimate is significantly different than 0 or not.
I see.
Yeah, because you would never fit a model that does not have a signal at all.
Understood.
Right? Yeah. So yeah, if it turns out that delta is still positive, they could end up with a positive estimate, even though there isn't supposed to be any signal in the data.
So this is what I think Shauli was talking about, right? I mean, even if you have, you could still get a case where the hypothesis does fail.
No, I think what Shauli was saying, that when we are comparing these two tests, there could be data sets like the same data generating process, but due to statistical fluctuations, there could be a data set where we do end up rejecting the null hypothesis when testing for eta tilde, but in reality, eta was actually 0. So yeah, so statistical fluctuations could give you such weird data sets where you still get what you are not supposed to get.
But this is a different case where your specification of the model itself is leading to
correct. Yeah.
The breakdown of it.
Yes, and in signal search cases, this is a usual problem, because no matter how much accurate we try to be about the background distribution, we are still, at the end of the day, if you are doing a maximum likelihood estimation, at the end of the day, we are still proposing a misspecified model. It is not the true model. Yeah.
But again, Charlie was saying, if you were to use a Bayesian formalism and try to calculate posterior, you don't
Yeah.
have this problem.
Yes, that's correct. The interpretations would be quite different. Yeah. Yeah. So next we get to some simulation results. We simulated some power analysis and stuff like that, and we deliberately chose a setup where the delta for the safeguard scenario would become a positive. And the data generation process that we chose was, our search region was fixed between 1 and 2. The signal that we chose was a Gaussian distribution with a mean at 1.28 and standard deviation 0.02, and a background distribution, which was a gamma distribution. Okay. And as you remember, like, safeguard requires a benchmark model. So do we. We also need this QB, which is a guess for the smooth background density. So for a fair comparison, we use the same benchmark as our QB, which is this distribution, which is a power law distribution. We use this power law distribution as our benchmark model, and we implemented our method for varying values of lambda. If you remember, lambda is what determines how much of a bump you have in your GP in the signal region. The larger is the lambda, the larger is the bump. You cannot go overboard with the lambda. That would incorporate a lot of the signal in the data, and you are being unnecessarily restrictive. You cannot completely ignore the bump, because then you don't even know whether delta is negative, and you don't know whether you are making a conservative estimation or not. Okay. So this is what the setup looks like. The red line is the true background. QB is the proposal, like QB is a guess for the smooth background, and the green one is the actual density, signal density. And this is what we got in our results. So in safeguard, as you can see, it has a positive delta. We recorded the proportion of rejections over 10 to the 5 simulations. And the rejection rule was whether p-value is below 0.05 or not. So the significance level was at 5%.
So
Yes.
just so I understand, when you run the safeguard case,
Mhm.
you do the simulation without the FS, without the,
Yes,
but then you do the maximum likelihood fitting using that.
using the FS, correct.
Okay.
And
And
yeah, and we use the same, like, each of the 100,000 replications, we generate a data set from the background for the type 1 error simulation. At least we generate a simulation from the data from the true background, and we fit whatever model is required for the safeguard and for our method, and we look at what is the proportion of rejections at the end of the simulations. Okay, and so the significance level of the test was kept at 5%, which means we should ideally get 5% or below number of proportion of rejections. In case of safeguard, we see that the rejection rate is around 24.2%, which means there are a lot of cases where even though there wasn't any signal, it was still rejecting the null hypothesis, and that's just because this delta was positive. Now, as we kept using our method, you can see as lambda increases from 0.002 to 0.01, delta gradually becomes negative. And that's why we start out with a high enough type 1 error, somewhere around 29.1%, but then gradually it drops to 1.7%. And 1.7% is below 0.05. That's because we are proposing a restrictive test, a conservative test. We are more likely to not reject the null hypothesis.
can I ask a question?
Yes.
Just actually for David Van Dyke. David, do you think that this is the reason that the protocol method works, or rather, this is the basis behind that paper?
No,
Okay.
I mean, this is non-parametric, right? Protosov was I mean, Protosov is using a likelihood ratio test between two specified models, and then making the likelihood ratio test doesn't have standard asymptotics, figuring out the correct asymptotics, or not exactly, doing simulation studies to get the p-values or the significance thresholds correct.
Yes, but the correspondence that I was thinking of was that the way we did the simulations was to look at effectively null models where the complex component did not exist, but fit it with both. So this is kind of like what this safeguard method that seems to be doing, and it's producing a large type 1 error. So that's why that's why the F test might have been failing.
Well, the F test was failing because it's using the wrong model and the wrong asymptotics. Right? The F test is pretending the Poisson data is Gaussian data. It's pretending that the null hypothesis is in the interior of the parameter space.
Right.
The F test is just completely inappropriate for that problem. The only thing the F test has in common with that problem is that it's a model selection problem. Now, there's two models, right? And they're nested. Yeah.
Okay. All right. Okay. Sorry for the diversion.
Yeah, no. So next, moving on from type 1 error simulations, we move on to our power simulations. And in power simulation, we don't generate data simply from the background, but we generate data from background, from signal, and we mix it with 1% signal. Okay. So here, Safeguard has a high enough power, 92.3%. And as you can remember, as lambda increases, the bump in the GB increases, which means we're being more and more restrictive with larger lambda. And that's why as lambda increases, you pay with a compromised power. The power goes down. But this is something I've not shown in this table, but I have the table in my extra slides, which is if you go to power simulation for eta equals 2%, there even with lambda equals 0.01, and with a 2% signal, the power was above 90%. Okay. So now in this table, you would notice that the result that you have for the safeguard is somewhere kind of between what we have for lambda equals 0.002 and 0.005, right? And that is simply because if you look at these proposal background densities, and if you really zoom into the signal region, the blue line, the solid blue line is the safeguard method. And that bump in the blue line is somewhere between the bumps of 0.002 and 0.005. So with our method, we have the flexibility to be as conservative, as more conservative, or as less conservative as we want. Okay. Next, moving on to some data analysis. So from our Atlas collaborators, we obtained some data on Higgs to daimyon decay via the VBF process. And here the data generating process is assumed to be a mixture of a Gaussian signal centered at, again, 125 and standard deviation 3, and a background that is unknown to us. Now, our collaborators suggested that we use a background that is proportional to, sorry, I need to put my laptop on charge. Just 1 second. All right. Yeah, as I was saying, our collaborators suggested that we use a background, like at least the guess for the smooth background, it should be proportional to what they call is a bright Wigner distribution. We call it something, we call it a Cauchy distribution. So it should be proportional to this Cauchy component plus a power. So I did that. So it's not the density. it's normalized so that it integrates to 1. And we had 4 categories of VBF data where we applied our method. We found significant amount in the VBF medium category, and that's what I'm presenting here. So this is what the setup looks like. This is our QB, the benchmark model, or the standard or the guess for the smooth background. That's the brown dotted line, and the green line is the signal density. This is so this is how we are proposing to implement our test. So the result of our test would depend on what value of lambda you use, right? So we suggest you perform a sensitivity analysis. Firstly, at lambda equals 0, where you are not even being conservative at all, if you see no discovery, if you see a high enough p-value, we would say that there is no chance that you are going to get any p-value over any discovery over here. Okay. But if you see a rejection at lambda equals 0, a p-value below whatever is your significance level, you can keep on increasing lambda to a certain point where you at least start to see these prominent bumps in the signal region. Okay. And then wherever you see there is a prominent bump and also there is a rejection, you can stop there and say, okay, we have some sort of a discovery. So for example, in our exploration, we increased lambda from 0 to 0.05. And even at 0.025, we saw that, so lambda equals 0.025 in the picture is the dotted red line, okay? And if you look at this red line, that has kind of a sufficient bump in the signal region, and also it's giving us a p-value that is below 0.05. So we do have a discovery at 0.025, but we can, if somebody prefers, we can choose to be more restrictive and even go beyond that and go up to 0.05, which is the purple line, the outermost line. That is the most restrictive one that we are proposing. And even there we have a discovery. And as for the safeguard method, you can see that they are also rejecting the null hypothesis with a p-value of 0.002. And the estimate for the safeguard method, understandably, is a little higher than our estimate at 0.025. So we estimate the signal to be around 8%. They estimate the signal to be around 8.9%. Yes.
Question. So you're calculating these p-values at different values of lambda.
Yes.
How does this get around the
Can I
multiple?
go to the gym this afternoon?
Sorry, Josh.
Yep. Oh,
Hey, Josh, did you have a question?
no question. Nice talk, though. Keep going.
Sorry. So
Yeah.
So how does this get around the multiple hypothesis issue?
So we're not suggesting that you look at this is one potential problem. You are kind of performing the test over and over again, and yeah, so this is one issue that we are kind of yet to discuss. What we suggest, the best solution we have as of now is this, and this is what we are suggesting. You go up to a point where you see a large enough bump and you are able to reject the null hypothesis. That's where your discovery is. You don't need to go beyond that. But if you really want to be more conservative, you can go beyond that. And yeah, that's kind of the best solution we have so far. There could be more objective ways to avoid the multiple hypothesis testing case, where you probably look at a plot of, let's say, lambda versus p-values and kind of cut off the lambda wherever you see a p-value getting below the 0.05 level, something like that. But yeah, this is still kind of in the experimentation phase, like how to implement the test. But so far, this is what we have. Yeah.
So if I may add something, so ideally one would create this plot on the right-hand side without even looking at the p-values, ask
Yeah.
maybe somebody like QVNA, oh, does the purple line seem to be reasonable in bounding the truth? And once you set a value for lambda, then you do the test. But if somebody wants to do multiple tests, of course, you should adjust for multiple hypothesis testing, but I wouldn't expect a person to do 1,000 or hundreds of tests. You're probably going to do maybe 10 at most, and in which case Bonferroni correction is fine, typically.
Yeah. Correct. Okay. So this is what we have from our VBF analysis. Finally, some last point discussions. So one of the main contributions of our work is that we have understood how the geometry affects the signal discovery. We have understood the central role of this delta quantity in determining whether what you are estimating is conservative or not. Because with maximum likelihood estimation processes, we could not answer whether we are being conservative or not, right? Safeguard method and spurious signal method, they also try to be conservative by injecting that signal like bump into their background. But as we saw, they still could end up with a positive delta, which in turn causes false discoveries. So as a remedy, we approach a heuristic approach so the mathematical basis is there, but then to satisfy that mathematical argument, we propose a heuristic approach where you keep adding this bump to the GB and you kind of visually assess whether the bump is good enough or not to dominate FB in the entirety of the signal region. And that kind of ensures that delta is negative. And we perform a conservative inference based on that without even knowing what the true background density is. Now, the better is your guess for QB, the better is your sensitivity analysis. Because at the end of the day, when you're comparing those bumps, you can always compare your GB with a bump as compared to the GB that has lambda equals 0. And you can see whether it is completely covering that lambda equals 0 curve in the signal region or not. And if your QB is like really close to the true background at lambda equals 0, your GB is QB. So the lambda 0 case would then be a very good approximation for your background, and you can perform your sensitivity analysis a lot better in that case. And lastly, so there could be cases where you don't have enough sample size, and that is not the best case for large sample tests. In that case, we propose instead of the usual non-parametric bootstrap, we could use the smooth bootstrap tests. And that's also one alternative. So lastly, I would like to thank the CHASC collaboration for inviting me for the talk, and I would like to thank the DSMMA program at our university for sponsoring my visit here. Yeah, thank you. That's it, and let me know if you have any questions. Thank you.
All right, any questions?
I have one which is mostly how would you make a choice for the proposal for the background model?
Yeah, so
Maybe also, I don't know, your computer picks up my sounds. Maybe you can repeat the question.
oh, okay, yeah, right. So the question is, how do you choose the proposal background, which is, I'm guessing that you are talking about this QB component in our proposal background, which is the primary guess for the thing. Yeah, so there are a couple of options. As of now, what I've done is I start with a parametric form of QB, let's say an exponential or a truncated exponential distribution or a truncated power law distribution. And I simply fit that through the data that has the signal. Okay. That just gives me an estimate for whatever the parameter is. So that's a primary starting point for me. That's what I feed into the GB and then keep on adding that bump, because the QB won't have any bumps because we are parametrically kind of restricting it to have that monotonic shape. Yes, I think Shaoli has a question.
Go ahead, Charlie.
My question is actually similar because I was very curious that the suggestion of you using this Cauchy distribution
Yeah.
as the thing, because so such a coincidence. I was just giving a talk at this German
Mhm.
conference. They were talking about Cauchy distribution. I asked the audience, it's audience about like 200 people. I said, has anybody fit the Cauchy in real life? There's only one person raised a hand. So I was very, very curious to see the Cauchy. And now, of course, this Cauchy is on the truncated region, so you don't run into the usual problems. But nevertheless,
Yeah.
I'm curious, like, was this entirely empirically fitting, particularly with this very odd x minus 1.55, or there was something else going on that suggests this
So
family?
So our collaborators actually gave us with the full specification of the Cauchy component. So they gave us the values that 91.2, 2.49, all those values. All I did was I added, let's say, this plus x to the negative k, then normalize it with respect to the entire search region, and then fit a log likelihood, then fit the log likelihood model and get an MLE for k. And that's what I'm using over here.
I understand it. Do you know why they choose the Cauchy? Was there
Uh,
something physically
so
meaningful?
So what I can remember is that when they are looking at the background processes, uh, the peak that they get for their background processes is outside the search region they have, and the tail for that background process is quite thicker as compared to what you would get for a particle discovery for the Higgs boson case, and that's why I think um, they use a Cauchy distribution where the peak of the Cauchy distribution is well outside the search region. For example, over here, the peak is at 91.2, but our search region starts from 110. So we are only looking at the tail of that heavy-tailed distribution, which gives us something closer to a power law distribution or a exponential distribution. Now, there were a few more specifications, but due to my limited understanding of physics, I kind of forgot what those arguments are. But something on this line, I think that's why they were using this Cauchy distribution.
I can certainly understand if using Cauchy to fit the heavy tail, but there are plenty of other, right? Plato, log normal, other things. All the astrophysicists in the audience, anyone can provide some insight? I'm curious because I love to see some real reason for the Cauchy.
Charlie, we use the Cauchy quite, in fact, generalizations of the Cauchy, which we call the beta profile, which basically includes an additional power in the denominator.
Okay, I see.
For example, we use that to describe line response functions. That is usually how a standard Cauchy is what the profile of a undoppler broadened line looks like, spectral line. So yeah, it appears the Cauchy appears quite a lot in astronomy.
Right, that's based on the kind of the Paul laws thinking, or this based on some physical reasons, derived.
That's usually the way in the case of the spectral lines, it's a consequence of Heisenberg's uncertainty principle. You have a finite width to a transition, and because of that, you convolve that with, let's see, what is it? With I forget how exactly it's derived, but I think when you convolve it with the actual point to point, energy to energy transition profile,
I see.
you end up getting a Cauchy.
Okay. That's good to know.
I forgot how we actually used to do that. There were some grad students here. Maybe you know about. Yeah.
Thank you.
Okay. Any other questions from anyone else on the? So if not, that's good. So we thank you, Aritra. This was a very fascinating talk. We could sit here and argue over your actual choices about of particular values for each one of these.
Yeah.
That's perhaps for a different talk.
Yeah.
Okay, so if there are no other questions, I'm going to turn off the Zoom recording at least.